Okay, now it's okay. I need something else. Now it's sharing only the iPad. Okay. Even if help, I'm gonna be here.
Okay. Yeah. Oh. I don't know why. Day.
8. Day 8.
Day 8.
Yeah.
So we skipped 7 though.
No,
I mean, we're 1 day short.
I don't know. It's day 7. I don't know which day it's today.
Oh. Are we going?
No.
Oh, okay. That works. Do we have anyone?
Yeah.
Oh, okay. I need my laptop. This is
quantitative structure, activity, relationship, statistics, introductory statistics seminar, day 7 or 8, depending on how you count. My understanding is we have today seminar, and we have Thursday, jueves, and then we are done. With the let's see. Today and Thursday, and possibly makeup. Either probably not using this online interface, but certainly if people email, we can arrange a time and an interface, and perhaps have a discussion session online via the Cisco GoToMeeting.com is a free thing. So I don't know. I will check. There may be a Thursday, I suppose, or perhaps via email or something, a evaluation. So that would be a evaluate that seminar participants were alive and watched much of the seminar, listened to topics, mostly you could call this a test, but I would rather not do this, but I think that we should do some kind of evaluation, essentially aware of the topic, and you know what the topic is, like very basic. I have not prepared anything, but this would be a way of evaluating that that people participated, were watching the seminar, not necessarily that you know a regression equation. So nothing technical, and I don't know what a criteria is, but maybe something like identify the topic, simple. simple, basic. Yep, okay. So Thursday, there may be this evaluation stuff, or maybe not, but also I would continue on Thursday. I have the intent, I intend to continue from today. So this will be a survey of topics, description, of methods. Okay, I'm going to go back. Yeah, so I apologize for the using the iPad interface. Writing on the iPad means that I am sitting watching a computer screen. Actually, I have 3 computers in front of me, and this is very different than standing up at in front of the room and teaching, and apparently it's makes it very boring for the audience. I know my wife attended the topology seminar, and she said she felt sorry for John because she kept falling asleep, and she said that it's all because of this iPad. So anyway, it makes me I don't tend to get excited and moving around. I just talk very monotone. So I apologize for that. So today I would like to I would some other things. Linearity. Okay. One more thing, I can't remember. Okay, so I would like to spend less than the full time, maybe half the time, working some sort of simple, basic, practical, looking again at linear regression. And so I have in mind to take a look at how the model is, when you do a regression model, how it shows how the results appear. And so the parameter estimates, and how do you use the parameter estimates? That's the interpretation. What do they mean? What are the parameter estimates? Then there are the just very descriptive, a little bit of idea about the statistics associated with the parameter estimates, and also in I will probably talk some about making decisions about the modeling, And then I have to, there's two other topics that I really cannot get away from linear regression without some brief coverage to talk about the R squared statistic, the reduction in the variance. It characterizes how well the model is helping explain the randomness in the data, or the variance in the data. So that's one another point. And then finally on that is this says collinearity. There's, which I will mention as anyway, I will try and explain that. Then I would, this is difficult for me to plan these last two seminars because there is still some nice introductory material that I won't be able to get to, and so it's difficult for me to decide what things to discuss. But anyway, we will look at various topics. I hope to have an hour to talk about methods, other alternate methods. This means, by alternate methods, I mean something other than, something different from multiple linear regression. And then I would like to introduce modeling some concepts about performing modeling work and validating models, and how the modeling, some of the ideas, although that I might cover some of that, model concepts. This is basically the same that this is the part that I would hope to continue with this on Thursday. Okay. I will be trying to show some things on the computer screen. I will be trying to show some examples for regression modeling from PDF files, and I'm not exactly sure how that's gonna work. I'm looking at some notes right now, and I'm finding the files on regression. One thing I can do is along the lines of makeup session or additional material is perhaps I will, if people are interested, please email me, and I can put together a list of reference material I have a lot of references on both basic statistics, but also in particular QSAR modeling statistics, some of which gets very, very complicated, but linear model. Okay, page 16. Trying to find, this is there's a book by Faraway. Let me see here. Regression. Let me find it. Okay, here it is. There's a nice book. And ANOVA using R. R is the name of a software by author Julian Faraway. If I teach the graduate level statistics class again, I will. I may try and use this book. I like the book. I like the discussion that this book offers. 2002 is what I'm looking at, but I believe there's a newer edition. Okay. I'm trying to find the example that I had. When to use all right. Let me go to a new page. Okay. So let me multiple linear regression. So I will note first, just aside, some people may be familiar with ANOVA analysis as part of, typically this is part of a basic, intermediate, I guess, intermediate level statistics, well, discussed in basic, introductory, and intermediate level, and then also in experimental stats. And just I wanted to make the point that ANOVA analysis is a linear model, and it is mathematically fundamentally equivalent to multiple linear regression. And this is a sometimes, how do I say it? Very often, statistics classes present ANOVA analysis as a fundamentally different topic, a different method as compared to regression analysis, and that's that I do not like that, because fundamentally they're the same. They're the same linear model. I mean, there's so anyway. So do not be confused if you the terminology and the expressions are different doing ANOVA, but it's really the same thing. Okay, so let's assume we have a basic regression model, which we express, well, a note, I need to check. One moment, please. Code engineering. Okay. So we had some response variable y that we wish to model with a basic 3-parameter linear model. So we have plus beta 2 x2 plus error. So we assume that this is the model equation. The E represents error term, or where data differs from the equation. This is the adjustment up or down for the actual data. And the parameters in the model are the betas. And we have then also, we have a we have two explanatory factors. Factors in this model. The two factors are x1 and x2. So this is something where a unit of data, there's a y value, an x1 value, and an x2 value. And we want to use the x1 and x2 values to explain the y value, explain the response variable. And so we had examples like the kilometers of usage of the used car, how many kilometers. So does the car in the advertisement, does it have 40,000, 40,000 kilometers, or does it have 197,000 kilometers? And the year of the make of the car. The year might be handled as either a numeric factor, a number with a linear relation to the number, or could be handled as a categorical factor, which I will explain a little bit about dummy variables in a minute. But this is our basic linear regression model, and that comes from having data that y, x1, x2, we have a sample, 1, 2, 3, sample size n, different units. which this could be the car, the advertisement for the car, or this could be a single car, or this might be a molecule. Each one. And in total, generally speaking, this is a sample of units which bear some degree of independence, which I'm not going to define that too clearly, but there's some, like, different people behave differently. They behave independently, but a class of people might behave similarly. So there's within the class, there is similarity that is what you want to model, and there are differences of the individuals within the class, like different people. If a class is students at USFQ, there are aspects, there are characteristics of the students which are the same based on the fact that they are USFQ students. And there are other things that are different about individual students, and so you have this within class similarity that you may want to take advantage of in the modeling to explain things, looking at all the individual variability within the class. Okay. And these quantities, these are numbers, especially the response variable, the response variable, or the dependent variable, or in sort of pharmacology, pharmacokinetics, pharmacology studies, medical studies, and I see it also in QSAR, the endpoint terminology. But fundamentally, it's the thing that you want to model. You want to explain something about this, and it is a number. It must be in the context of multiple linear regression. There are categorical regression models, but that's a variant, an alternate form. So this is a number like 100 or 0.01 or -4. And the x values that go, the x explanatory factors must be numbers in some sense internally when the software computes anything, it computes the regression model. These things must be numbers. The model is solved using numerical linear algebra internally in the computer to solve the equations, and it needs numbers, but it doesn't necessarily have to be numbers in the natural sense, and that's where I will talk about dummy variables and factors in in just a minute, categorical factors. But for now, you can assume that this is some numerical quantity for these things as well. And each one of these, like 10 and 20, 100, 10, and 20. I'm just going to plug those numbers into a fake equation. So 100, that's the y value, equals, I forgot, 10 and 20 is beta naught plus beta 1 times 10 plus beta 2 times 20 plus some error that's positive or negative. And this error term is where the statistics and probability distributions enter this world. And x1 is there, and the x2 is here, right? Going back, I just made some imaginary data to show where how the numbers fit into the equation. And then what the idea is in the modeling is that the model parameters are the things that are estimated. And we want to find out what those are so that we can give our interpretation and know the behavior of the model. And these values, these model parameters, the beta parameters, are the target. We wish to estimate. That's what the modeling is doing. We are estimating the betas. That means, okay, hold on. Now, I wish to note that the beta, whichever beta it is, the parameters of the model are fixed values for the model. It is there, let's see, for this model that we're looking at, there are 3 parameters and there are only 3 values. The parameter values are something that are associated with the model, not with individual data. So if we go back and look at a listing of lots of data, where we have, I wish it would keep the same color. Here, different data points. All of these data lines are feed into the model, and they all, the model uses, the calculations use all the data to estimate one set of parameters. So that's 3, in the case here, that's 3 specific numbers. We don't change the beta parameters depending on which data line it is, right? There's just one set for the whole thing. And that's what we call this the parameter estimates. I will show some, introduce some notation. This is the caret, or the it's number 6. What do you call that what do you call the caret in Spanish? Look at number 6 on the keyboard. That thing. No, what do you call it? Oh, no, it's different. I knew it was going to be different. That's why I was asking. I don't see it. Okay, but I won't worry about it. This symbol. In stat, people call it. Okay, sombrerito, the little hat, which goes nicely with statistics terminology, because in statistics we call this the hat. So, it's called a caret. If you have an English language keyboard, it's the number 6 above the number 6, but forget that. Okay, so this is just notation. When people write an estimate from the model, an estimate of a parameter, or an estimate of the prediction estimate of the response variable, the y, so either a y that you're trying to model, or the betas. For these things, statisticians, and most of the papers that show modeling expressions, they have the hat. So we say y hat is an estimate of the y value for specific x values. So that's given some specific x values. You can plug those values into the model equation and get some number that is probably different than the actual data point. Okay, and the difference is the error, and so y hat is the prediction of the model, and the difference between y hat and y is the error. That a specific, if I call it the ith observation, the specific value, like 100, for the y value of a specific data point, that is a data value, right? 100 or something like that. And that differs from what the model estimates, because the model is giving you, telling you that it's beta naught plus beta 1 times 10 plus beta 2 times 20. It depends on what the beta parameters are, but it'll be a number, and it differs from the true data value by the amount of error for that data point. Similarly, we use the hat, so hat. Like y hat, or beta 1, go away, beta 1 hat. These are model estimates. So when we talk about the beta hat, this is the estimate. So beta 1 hat estimates beta 1. This is a specific number that when you take the data and you plug it into some software, writing something like LM, if we had the data in the software, and if it was something like R, or MATLAB is somewhat similar, SAS is very different. It all just depends. Some software has menus that you can use. I hate that because it's bad, but anyway, you can't validate what you've done, but you know. Programming is the right way to do these things. But in R, the software, you would write LM, and then you have to give it the name. You can say Y tilde X1 plus X2, comma, and then the name of the data, a reference to the data set. And this is a function, and it produces, it performs calculations. It's just the calculations are all just linear algebra, numerical approximations, numerical linear algebra. And it produces various objects, various output. What it does is it looks in the data set, and it finds, you know, all of this data, and it finds that there are variables named Y, X1, and X2, and this is the expression used in various software uses a similar form of this. It's a code to express the model, and this is telling it that I want a model that is estimating, or it's modeling y as a function of x1 variable and x2 variable, and oh, is that with a plus?
Maybe not. Just a second. Linear model, matrix representation. I don't want to give the wrong. Okay, well, we won't worry about the software too much. It will generate output. The output tells you, it gives you parameter estimates. It might tell you that beta naught, I'm going to introduce this name, the intercept. Often software will call this the intercept. So you have a beta naught factor. It's not a factor. It's just it's something that's estimated. It's the intercept in a straight line function. Right? There's the intercept, the y-axis intercept, and it will give an estimate for beta 1 and beta 2. These will normally be labeled with the name of the variable that's in the data set, whatever the name is in the data set. We'll call x1 and x2. This is not the x1 and x2 values. What we're talking about here is the parameter estimate for the beta associated with the x1 factor. And you get some numbers, some estimates, like an intercept of 50 for beta naught. This is equal to beta naught hat. It is the parameter estimate for the intercept parameter. And for x1, maybe, I don't know, whatever, we get -1. So that is our estimate of beta 1. So it's beta 1 hat. But this is what will normally show up in the software. It doesn't say beta. Beta is what we use when we write down the equations. And x2 we'll say is, it gives a value like 2. And so that is our beta 2 hat. Now, these are estimates and they are statistical quantities. The reason they are statistical estimates is that the value of the beta factors, the results of the model depend on the particular random aspects of the sample. And a different sample of the same population will have different data. If we were, well, whatever. If we wish to model something, using, you know, the model that we wrote before, the result of the parameter estimates, the statistical quantities, will depend on the data that we happen to have in the sample that we are using. And it is a random variable or a random quantity because a different sample will have different units that are sampled, and those different units will have different x1 and x2 and y will have different data values. And so you plug all the, for the specific sample that we have in our data, all these numbers go into a matrix, and it solves the equations and gives estimates for the parameters. But there's some variability associated with them, and because it is a sample-based random quantity. And that is the point. It is in terms of these, it is for these betas that we were talking before about inferential statistics, because we would like to know, we estimate, so beta 1 hat estimates beta 1. Unless we look at the entire population, we will never know what beta 1 is. All we can do is look at beta 1 through its estimator, beta 1 hat, and the statistical aspects of this estimator. So just like a sample, if we go back and you think of just a simple sample of students, sample of student height. We sample 100 of many, 10,000, 5,000, many students. We sample 100 of them randomly, and we have height values. And we can look at the average of this sample. X bar as the sample mean. And we talked about before, I did just the very minimum introduction to be able to discuss, to be able to get into betas and models. So the sample mean is a statistic of the data. It's something that's calculated from the data, X bar, and X bar, the sample mean, estimates the population average height. And we do statistics on this, inferential statistics, with hypothesis test, p-value hypothesis test, like a hypothesis that the population average equals 150, mu equals 150. Alternative hypothesis, mu is greater than 150, and our sample gives us some information to be able to evaluate this statement with a probability assessment, which is the p-value, and an equivalent alternative way of expressing these things. Instead of a hypothesis test, we might make we would do both, right? We would also make a confidence interval. Something like a 95% confidence that the population mean mu is between here and here. Okay, maybe 150 is down there, and so we missed it. That's equivalent to a rejecting the null hypothesis in favor of the alternative. Okay, fine. So that's just looking back at what I tried to show before with the basic statistics, basic inferential statistics, and we will do the same thing, but now the statistics, or the thing that we're estimating and that we're doing statistics on, is the model parameters. But just like our sample of students, these model parameters depend on the sample. If we had a different sample of students, right, we sampled 100 students. If we had a different sample of different people, we would have different heights, and those values would have a different sample mean and a different sample standard deviation, and we would have a different result in terms of a p-value, or a different confidence interval. Maybe we would have a confidence interval down here. Right? The same thing happens with the model parameters. So go back. Boy, I am not going to get through this. Okay. So we have beta not hat. This is the intercept estimate. Beta 1 hat is the beta 1 estimate. Beta 2 hat is the beta 2 estimate. And okay, I need to make some kind of real world model. I mean, fiction, but related to a natural thing, to be able to discuss this, the interpretation. But with these things, there is a number for the estimate. Just like the sample mean has a value, the intercept estimate and the beta 1 estimate and the beta 2 estimate. These things have values. You know, what did I say? -1, 2, and -1, 2, 50, -1, and 2. 50, -1, and 2. Okay. This is the estimate value, just like the sample mean is a point estimate. But these things also have what you call a standard error. And you can look at things like a p-value, which is an assess or the confidence interval. 95% confidence interval, which these things depend on the standard error, and these are what we use to make our inference about the parameter. And we might say something like a null hypothesis that beta 1 equals 0, and an alternative hypothesis that beta 1 is not equal to 0. And if we have a small p-value, like 0.002, then we reject the null hypothesis, and we conclude that the beta 1 parameter is non-zero. This has some meaning more than, that's not a stupid, trivial thing. That means something. And what that means is, if that is non-zero, well, the question of whether beta 1 is 0 or not equal to 0. Is very important because it tells you whether or not beta 1 is useful in the model. So let's look at y equals beta naught plus 0 times x1 plus beta 2 times x2. This is where we see if beta 1 is 0, then the model does not have any number result, any impact associated with the x1 factor. So when we have a parameter estimate that is close to 0, so maybe beta 1 hat equals, what did I say, -1, and there's another column in the output very often giving the standard error of the estimate, and that might be 4. And that is, this is the standardized quantity. I won't explain too much, but a confidence interval using the estimate and the standard error of the estimate, a 95% confidence interval, ERVAL interval, for beta 1 is -1, the estimate, right? plus or minus approximately 2 times the standard error of 4. So we've got -1 plus or minus, oh, sorry, wait. We have beta 1 hat plus or minus 2, this is approximately 2, times the standard error of beta 1 hat. Just like the standard error of x bar, which the standard error of x bar is often called the SEM, standard error of the mean. This is the standard error of beta 1 hat. And if this is, so if we have -1 minus, what did I say, a 4, minus 2 times 4, that's the lower end of a 95% confidence interval. The upper end is -1 plus 2 times 4. So we have -9 and 7. So we have a confidence interval, there's 0, that -9 and 7, and these are reasonable values for the theoretical parameter value. We are estimating that the true population parameter for this modeled parameter is somewhere in here. Similarly, because of the equivalence, we could do a hypothesis test, H naught, null hypothesis, beta 1 equals 0. Alternative hypothesis, beta 1 is not equal to 0. And with the equivalence, we would not have sufficient evidence to reject the null hypothesis. We don't have a statistical reason. We do not have strong statistical evidence to claim that this 0 value is wrong. We can't say that this is wrong, right? Because it's in our confidence interval. That's 95%. So we know that the p-value, because the 95% confidence interval, that's a 1 minus alpha percent interval. Because the 95% confidence interval includes the null hypothesis value, that's the H naught, beta 1 equals 0. It includes that, that's the 0, right? Right there. Okay, because the 95% confidence interval includes the null hypothesized value. This is, let's see. We fail to reject H naught at a significance level at the alpha equals 0.05 significance level. So what I am saying is putting together a little more together than maybe what we talked about before, but all the pieces were there. So I'm not going to explain too much because it would take too long. I'd rather get to some other stuff. Okay. So this is important because if beta 1 is 0, then the x1 factor does nothing in the linear model, right? I was showing that before. Beta naught plus beta 1 of 0 times x1 plus beta 2 times x2, right? This 0 cancels this term. It's like it didn't exist. It is 0 always. It contributes nothing to the model. Therefore, in this situation where we fail to reject the 0 value, we fail to reject it. We do not have any statistical evidence to suggest that beta 1 is non-zero. Therefore, we have no evidence at alpha equals 0.05, right, level of significance. We have no evidence to say that beta 1, well, stop, to say that x1 is a significant, is a useful factor, a useful linear factor in predicting or modeling, in modeling why? Okay, so that comes from our when we have null hypothesis, beta 1 equals 0, and we fail to reject, or we look at the confidence interval, covers 0. So we failed to reject. It's the same, means the same thing as the at 5%, means the same thing as the 95% confidence interval covers 0. So this, the interpretation there is that leads you to assume that there is no useful, I'm just the same thing I wrote before, no useful or no statistically, let me be more proper. Well, in the context of QSAR modeling work, this differs from experimental statistics work, very much so. But in QSAR modeling work, you're trying to develop the right model that fits the data and has explanatory power. Explanatory power is the terminology often used, meaning it has some useful statistical power in explaining the response variable in the model. So looking at, we had a model where we were relating the response variable y to an x1 and an x2 factors. And if the beta naught parameter, if beta 1 is 0, right, if more or less, if it's about 0, then x1 is not a useful linear predictor, or it has no explanatory power in the model if it's 0. If it's, okay, so because we can assume beta 1 is 0, therefore x1 is not statistically significant. It's not statistically significant in the model. Now, that does not mean that it's useless in this more general conditional probability sense. It doesn't, so let's say that beta 1 is 0. This is not saying that, well, hold on. I will draw a picture of beta 1 is 0, where there is no linear model, there is no linear model significance. But x1 is maybe still predictive. Okay, the picture of this is an example. A picture would be like a nice set of data where we have an x1 value, and we have a y value. And this, over this whole domain, there's no linear correlation between x and y. There, in this half, there's a very nice linear correlation. And in the right half, there's a nice linear connection. But if you model the whole thing across the entire domain of x, all these data points, there is no good line through all of it. This is the line that the model will predict. It would look exactly like that. And this is the slope of this line, delta y over delta x1, is 0. Right? It's horizontal. There's no change in the y value. And there is no linear significance. There is no linear value. There is no explanatory power of beta 1 of x1 factor in a linear model. But there is very clearly a relationship between x1 and y. So this is where a linear model is a nice idea but doesn't fit the data. This would need to be in a situation exactly like this. You would model it as two different data sets. You would break it right here. But very often you have things that look like this. Here's x1, here's y. You know, you have data that's something like that. It's a parabola. And if you take the square root, then you have a linear function. And you can model, so you would not necessarily see a linear relationship, but if you look at the, remember I referred to the scatter plot matrix, looking at all the relationships between the variables, and some of them might be a reasonable straight line relationship, but some things might go like that. Sometimes, very often, with demographics and people kind of data, you get a relationship that you might have data like this, and some more down here, and you have something that is, there's no clear linear relationship over the whole domain, but when you look at this picture, you see, oh, well, I have something going on here and something here. Both of those things are somewhat linear relationships, but there's two different groups that need to be researched. Okay. Now the okay. Yeah, this is, I'm sorry, I'm going very slowly, but you can, if you understand this part of it, then you can go on and read on your own more things. Okay, we will take a break and come back to interpretation and then some other stuff. It is 5:33. We'll return at 5:45, 5:45. Thank you.